My name is Omar Farooq, and I'll be presenting the prediction of diabetes, hypertension, and stroke using different machine learning models like logistic regression, decision tree, random forest, support vector machine, and KNN. So this is our introduction. You can read through it. Let's set up our environments. I'll be installing some libraries. As you can see that we're using pandas profiling. We might use that at some point. And these are our libraries that we're going to be using in our uh, workflow. Similarly, these are our data sets. Since I'm predicting three different things, I'm using three different data sets for it. So we're going to deal with them one by one. So this is our diabetes data set. We have loaded the data set, and we can see the head of the data set, which is like the first 5 rows. Everything looks pretty much fine. And this is the shape of our data set. We have got like 70K observation with 18 variables. So before any further ado, let's look for any missing values or duplicate values so that we can fix those before starting exploration. So we can see that there are no missing values, but we've got some duplicates. And if you look at the duplicates, which is like less than 1% of the total values or total observations, so we can easily impute or remove them from our observations. After that, we did explore the data. So this is our target column, which is the diabetes column. As you can see that we've got more respondents which have diabetes as compared to non-diabetic. So after that, we move down to age group. We've got different people from different ages. Over here, one actually represents a particular group. It's not a real number. One is people from 18 to 24, similarly all the way to 9. Then 9 is from 60 to 64, and then all the way to 13, and 13 is 80 and above. So as you can see that as we go above the age group, the number of respondents have more diabetic, and number of respondents non-diabetic also increases, but like it decreases at a certain point. All right, this is our contingency table. Contingency tables are pretty good in handling categorical or representing categorical data. So it gives you the exact number of how many people are diabetic in an exact age group. So let's say we have got age group 1, so there are like 814 non-diabetic and 78 diabetic people in that age group. With the age group 9, which is age group 10, which is from 65 to 70, we have a lot of respondents who were diabetic, which is a common thing to happen. Similarly, this is our gender distribution. We've got a lot of female respondents compared to male respondents. In both cases, we've got more diabetic respondents as compared to non-diabetic. Here's our contingency table. You can look through the exact numbers. Similarly, we have another column for high cholesterol. So people with higher cholesterol tend to have higher percentage of diabetic. In this particular case, we have like higher percentage of diabetic with people who have high cholesterol. 0 means like no cholesterol, or cholesterol less than 170 mg per dl, or 1 means like cholesterol that is higher than 170 mg per dl. 170 is a normal range. And here's our contingency table. Similarly, heart disease. So people with heart disease, again, we had less respondents as compared to people without any heart disease. But with people who have heart disease, relatively have higher number of diabetic patients. Similarly, again, contingency table. Smoker column, it might not be a very good predictor. As you can see that we have got pretty much equal number of smoker and non-smoker, and the variation is very less between smoker and non-smoker in terms of diabetic and non-diabetic. Similarly, people with physical activity. So physical activity could be a kind of a predictor, but people who are less physically active have a higher percentage of diabetic patients in it. So here's our contingency table. Heavy alcohol consumption. Well, generally we would think that like alcohol might increase the the number of diabetic patients. People who consume alcohol might have diabetes, but in this case, if it was proven not to be, and the data is mostly from like non-alcohol consuming people, so there are only few respondents who heavily consume alcohol. So it might not be a good predictor, but we'll have to check that in our correlation plot. Similarly, people with their general health starts from like 1 to 5. 1 stands for excellent and 5 stands for poor. So as we go from 1 to 5, the number of diabetic patient increase, kind of decrease at the end, but that's because of we have less respondents from that particular group. Similarly, here's our contingency table. Mental health might not have to do anything with diabetic, but we're gonna still look at it. Mental health over here translate to people who have any kind of hypertension or any kind of depression in the past 30 days. So as we can see, that a lot of people are from group zero. So people might, a lot of people does not have any, had any hypertension or any kind of depression in the past 30 days. Similarly, physical health again might not be a very good predictor since we have got a lot of people from one group. Difficulty in walking could be a very good predictor since we can see that people with higher diabetic, people with diabetes usually have difficulty in walking, which can be proven from this particular point. Here's our contingency table. Similarly, stroke. Again, stroke might not be again a very good predictor since there's a lot of people from non-stroke history. Higher blood pressure, so people who have a higher blood pressure tends to have diabetes. And with a little bit of knowledge, we kind of know that from the doctor. We usually hear that on the TVs that people who have higher blood pressure or higher diabetics might have higher blood pressure or diabetes, vice versa. All right, this is the body mass distribution, as you can see that. And coming to our correlation. So here's our correlation plot or table, and after that we'll follow it by a plot. We can from here we can see that which particular feature or variable has a strong correlation. So we can see the high blood pressure has relatively a stronger correlation with our target variable diabetes. So we can pick this one, similarly this one, and include that into our model, and that's what exactly we did. Here's a heat map for the correlation. Similarly, these are our models. This is our machine learning model. Since we'll be using different kind of models, so I've created a dictionary of models and then used a for loop to go through that dictionary to pick up each and every model and evaluate the performances based on testing and training data sets. So you can go through the code. I'll share the link at the end. All right. So here's our model performances. As we know that pretty much every column was a categorical column, and we know that logistic regression is pretty handy in handling the uh, categorical data. So the accuracy comes out to be 73% for the training and testing data set. Testing data set is the data set that the model haven't never seen, so it's something new to the model. And training is already seen data. Similar decision tree performs really well on the training set, but it does not perform very well on the testing. Similarly, same is the case for random forest. Support vector is pretty close to logistic regression. And again, k nearest neighbor or KNN model again does not perform very well on the testing data set. Now moving on to our second data set, which is hypertension. I pretty much did the same process for hypertension too, so I might skip through that. I've checked for handling and missing data, again, the same pre-processing of data and then exploratory data analysis. I'll just go down to the results straight. So I went through like each and every column. I would add that to it. I actually used Regis plots for different distributions of data since we've got some continuous variables. So I felt like I should make some Regis plot, which is pretty handy to understand like what's happening in each category. Like let's say people who have hypertension over here and does not have hypertension, how is their blood pressure behaving? Similarly for the cholesterol, again, it's a continuous variable, so I did make some Regis plot. So you can see like people with higher cholesterol, what's happening with them compared to like, less cholesterol or low cholesterol people. Similarly, maximum heart rate achieved is the Regis plot. And then we have chest pain, chest vessels. So I'll just skip through it again. It's the same similar process, and then at the end we actually make a correlation plot or and table. So from here we can pick out the best or the features we have higher correlation with our target variable. Or we can also do that from the heat maps. Sorry about that. All right, so coming to our models. So again, we're going to use the similar models for this particular data set too, and pretty much similar code. So we can see that there's some continuous variables. So logistic regression does perform very well. It's up to 85%. And again, just to kind of confirm this, I've used the same kind of data set and same modeling in R, and I got the same kind of accuracy, pretty much the same. It was 86% as compared to 85%, so which is pretty close. Again, decision tree performs really well. We got like 100% accuracy, and followed by random forest and k nearest neighbor. They've got, since we've got some continuous variables, so those are pretty handy in handling continuous plus categorical data. Again, support factoring is not performing according to other, I mean, not according to our requirement, or maybe not according to like what are other models doing. All right, so I have a big conclusion at the end, so I'll just skip that. So now coming to a third data set, now we know that like doing exploration is pretty time consuming and it takes a lot of time. So in this particular data set, I've used something called pandas profiling, which is really great. With this one line of code, it gives you everything that you need. So when I ran that code, it gave me a complete exploratory data analysis. So when I run that code, I got all these statistics over here. It gives me the number of observation, number of variables, any missing values, any duplicates. And also at this point, sometimes it gives you another tab option over here, which tells you about the strongest correlation between, but in this case, we don't have any very strong correlation, some moderate correlation between variables. So that's why it does not give us anything over there. And that it takes you through every variable. So we can see that we've got like, let's say a gender variable or sex variable over here, which got two distinct values. One is 0 and the other one is 1. We've got more male respondents in our stroke data set than female. Similarly, age, this is the age distribution. Similarly, we've got heart disease, everything with one line of code. So it's a pretty good deal. And then at the end, it kind of gives some interactive graphs, so you can make and plot different parameters against each other, which is pretty solid. Similarly, it gives you a correlation table and a heat map, which is with one line of code. I would definitely take it, and some missing values. So we can see that our sex column has like 3 missing values. We can confirm that in a code coming up. So when we run our code, we can say there are 3 missing values. I can easily remove them. It's only 3, and then we can go ahead and check out our machine learning models. And this is pretty much the same code as we use for the other two data set. And we can see that the logistic regression performance is very low, since we're dealing with healthcare data set, and we know that everything has to be above like 90% first of all, but if not 90%, at least like 85. And this is way below par. So we'll just kind of ignore the logistic regression for these kind of data sets, for this particular data set actually. And then our decision tree performs really well according to our expectations. Again, random forest again almost up to 99% on a training data set, on a testing data set, and 100% on a training. Similarly, k nearest neighbors is not pretty much far behind. It's up in the 80s for the new, and 92% for the training. And support factoring is performing the worst. All right. Coming to our conclusion, so we saw that in we saw that in our diabetes data set, the variables that were actually helping us in predicting the diabetes were these, the ones that are highlighted. And the best model to handle that kind of data set was logistic regression. But keep one thing in mind, that we haven't tweaked other models. We haven't changed, like let's say if I change the hyperparameters for KNN, it might perform differently. I haven't done that. We can do that on the expansion of this study and find out the exact, like, hyperparameter for getting the best out of K and N. Or let's say if I can change, let's say maybe iterations in the logistic regression, so I might get a better result with the logistic regression. So I haven't done any of those. I haven't tweaked our model or fine-tuned our model. I've just checked the differences between model in its raw or in its like yeah, I would say in its raw form. Similarly, with our hypertension, the main features that were actually affecting or help us in predicting hypertension were these, the highlighted ones: blood pressure, chest pain, heart rate, etc. And the best model came out to be decision tree, random forest, and KNN, and its raw form, whatever you just saw in the code. Again, and finally, with stroke, we have got these parameters that were helping us in predicting, and the best algorithm was again similar to our hypertension data set. So this concludes our study. If you got any questions, please let me know in the comment. Thank you.